Hi, everybody. This is Dr. Ed Park, and today we're going to be discussing what exactly is in these exosomes. And as I often rely on this analogy, it's kind of like music. I always have to say that the use of exosomes has not been approved by the FDA for the treatment or prevention of any disease. This video is for educational purposes only. It's not an advertisement, and anecdotes are not scientific proof, rigorously speaking, although they are a form of evidence. All patients, including my mom, were treated within the context of an informed patient-physician relationship. Okay, just to rehash, exosomes are not cells. They are not stem cells. They're what the stem cells make in this case. So they're about 1/300th the diameter. They're only 100 nanometers, same size as the coronavirus. They contain mostly mRNA. Unlike the coronavirus so-called vaccine, there is no single message. There's hundreds of messages, both in proteins and messenger RNA, which we'll get into a little bit. They're not cells, so they don't have the machinery to reproduce, such as the nucleus. They don't have the ribosomes. They don't have any of the stuff that make them a fully functional organism. In other words, they're just the songs. They're not the musicians. They're not good or bad. In fact, much of the literature in exosomes scientifically is describing bad exosomes in cancer. So it turns out that when you have a cancer state, the whole atmosphere is bad and there are bad signals going around. And if you take exosomes from a person with cancer, give it to a lady without, she can start to develop malignant transformation of the breast. So there's this sort of ecological model of disease causation. There are other extracellular vesicles that are larger. Some of them, as you see above me, are from the breakdown of cells themselves. So that's not what we're talking about. We're talking about the things that are intentionally made to communicate with other cells. And to my left, you see the most important concept, which holds true. It's just that DNA, which is usually double-stranded, is the code for proteins. Everything runs on proteins. So the messenger RNA is the transcription. Yeah. So the messenger RNA is the message, and then that's fed into ribosomes, which will automatically translate the protein, which is why when you get a Moderna vaccine or whatever, the messenger RNA for the viral spike protein goes through your ribosome, just like any other message, and it produces spike proteins for your cells to express. All right, let's go a little deeper into cell biology. So zooming in, this is the nucleus. Inside the nucleus is the special nucleolus. This is where all those messenger RNAs are produced, unless you get them externally and they get into the cytoplasm. Cytoplasm is just the area outside the nucleus, but inside the plasma membrane. So that's the body of the cell. And so if these messenger RNAs come in from outside, as with exosomes or with this Moderna vaccine, Pfizer vaccine, then they can be expressed by these little dots, which you don't really see that well here. But what we see in the orange circle is mitochondria. These are those little bacteria that got in us a couple of billion years ago and produce our energy for us in a partnership. And then at the bottom, you can kind of see this rough endoplasmic reticulum. Rough because it's got beads of ribosomes on them. Those are the protein making machines. Endoplasmic means it's in the endoplasm or the cytoplasm. And it's a reticulum because it's shaped like a net. Ret is net. After the endoplasmic reticulum, we have this Golgi apparatus, which looks like stacks of laminated, I don't know what you would call them, folds or pleats. But budding off of these are the multivesicular endosomes, meaning usually exosomes are released in batches, like, I don't know, a dozen or more little balls within a larger ball. And this is where they bud off of the Golgi apparatus. This cell is taken from a pancreas. We see, look at how the RET, the net, endoplasmic reticulum is so rough and so beaded with all these protein factories, these ribosomes. And that is because this is a pancreatic cell. It's pumping out tons of insulin and other digestive enzymes. So you just have a lot of protein production. And look how juicy the mitochondria are to produce the energy to do all this. Zymogen granule above me is just, that's a digestive enzyme. Okay, so above me, the greatest, arguably, musician of modern times, at least in the moment, is John Coltrane. And so, you can't really say, well, what kind of music does John Coltrane make? He can make whatever he wants. In the case of different types of musicians. We have different types of stem cells, which under different conditions would react differently. We don't really understand stem cell consciousness or even cellular consciousness. We don't know why some days they decide to play certain notes and others. But anyway, here is the chimeric company's attempt to characterize their product. And what we see is a bunch of the common assays for proteins, and room temperature amnio is there, meaning just like without the exosomes. When you isolate the exosomes, the next product, which is kind of deprecated, they don't really use the amniotic fluid product that much. It's very, very different from the blood exosomes produced by, well, I shouldn't say blood, they're produced by the mesenchymal stem cells from the placenta. So very, very different numbers, very significant. This musician knows what it's playing. And so it's important to understand that exosomes until 12 years ago were just ignored, but there are exosomes in everything. Plants use exosomes, cow's milk has exosomes, kids that drink a lot of cow milk express a bunch of cow proteins, which may or may not be very similar to human, but they tend to do better on the Army fitness test, and they tend to be bigger and stronger. So what we do as we scan down this list, it's alphabetical, but this is by no means inclusive. This is like page 1 of 5. So when you say what's in an exosome, there's a lot, and it's not random at all. There's, 0 here of TGF alpha, that's inflammatory, and yet there's 340 times the concentration of TGF beta 3, which is anti-inflammatory. So we see definite trends in the music they're playing. The VEGF is vascular endothelial growth factor. Anyway, so the red is just meant to highlight what it's got a lot of. In keeping with the theme, the most popular jazz album of all time is, of course, Bill Evans' collaboration with Miles Davis. And you see 3 amazing musicians, Coltrane on the right, Cannonball, Julian Adderley in the middle, and Miles Davis on the left. And so this is the most beloved, most downloaded, most played album, Kind of Blue. And so these dudes could play whatever they want, but they tend to play certain things. So within the genre of mesenchymal stem cells, what we have is a regenerative anti-inflammatory message, and we'll again reiterate that with some specific evidence. As we kind of scan down this page 2 of what's in the exosome product, what we see in the red, there's a lot of interleukins. Interleukins are proteins meant to modulate or alter the function of white blood cells, okay? We also see a ton of TIMP, tissue inhibitor metalloproteinase. Metalloproteinases are, again, everything pretty much that works in the body is a protein, with a few exceptions. So the metalloproteinases are responsible for destroying tissue as part of the regeneration, we hope. But if you can stop and inhibit that, so much the better. Okay, here's another continuation, different printout, different results, just highlighting that, of course, exosomes are not the same as amniotic fluid. Exosomes from MSC are not the same as in amniotic fluid, and the concentrations vary wildly and purposefully. BMP is bone something protein or morphogenic protein, epidermal growth factor, VEGF, I mentioned, vascular endothelial growth factor, fibroblast growth factor. BDNF is much touted on these YouTube videos, brain-derived neurotrophic factor. GDF-15, another growth factor. GDF-11, popular as an anti-aging treatment. Growth hormone, hepatocyte growth factor. What's not listed here is stem cell growth factor, platelet-derived growth factor. NGF, there are a couple flavors, not seen here, but in other readouts, you will see it. Very important thing that shows up is osteoprogerin in the middle. That helps to maintain bone and build bone. Again, we have insulin that's showing up, insulin-like growth factor binding protein, IGF-BP. These are kind of like albumin in the blood. They allow the insulin-like growth factor to persist longer, so it enhances the effect of insulin-like growth factor, which is anabolic and trophic. Let's drill down on a couple of these. As I mentioned, bone morphogenic protein stimulates bone growth, GDF-11, 15, OPG, GM-CSF is granulate macrophage colony stimulating factor. This enhances the reproduction, the clonal expansion of white blood cells. My friend is undergoing chemo, and she gets a shot of this to keep her from natoring in her white blood cell count. stem cell factor, TGF beta 3, again, very important to shut down inflammation. And ICAM1, another thing that binds inflammatory ligands. So the trend is definitely, these guys, even though they're jazz musicians, they play in key. They know what to play. And the trend here is always shutting down inflammation and engendering regeneration and regrowth. This slide is courtesy of Dr. Spiel. Another page here, we have interleukins showing up again in the anti-inflammatory variety, macrophage activation IL-6, and we have monocyte chemoattractant protein. Again, that's attracting cells to come to the area. Platelet-derived growth factor, another prominent one. I mentioned the huge amounts of TIMP1 and 2, again, to reduce breakdown of tissues, hepatocyte growth factor, glial-derived and brain-derived neurotropic factor, again, helping nerve cells to expand and grow. And again, TNF-R1 to bind up the TNF-alpha, which is the pro-inflammatory molecule. Okay, so something really cool that I wrote about in my first graphic novel, and I write about a little bit in my first book, is this endosymbiotic event. And I think it's really important to understand what happened about 2.7 billion years ago. You know, there still are these protists, or one single cell organisms, bacteria, but they can't really make a go of it because they're not organized, yeah? So what happened about 2.7 billion years ago was that a little deal was struck, and the mitochondria were swallowed up by our little amoeboid-like cells, and it allowed the amoeboid-like cells to go differentiate in a bunch of different ways. They became, you know, specialized to different organs. And then the whole idea of embryogenesis and a complex organism was engendered by the fact that we had someone else outsourcing our energy production, okay? And about the same time, it happened with plants. Plants swallowed up these, what do you call it, chloroplasts. And so the chloroplasts use photosynthesis to make energy for them. And so plants can be complicated and specialized and have, you know, sexes and genders and whatever. Same with animals. But when you look at single cell organisms, they don't have that level of specialization. So we look at, you know, algae and bacteria. They can't do the amazing things as easily because they're not organized into a larger system. And I think this beautifully for those who don't think or ruminate about the fundamental dogma, they call it, of biology. Here it is in a nutshell in these 3 slides. And what we see here on the top left A is that a protist, or a bacterium with a single strand of DNA here, it's often circular, but the point is that what comes off the DNA perpendicularly are these little messenger RNAs. And on the messenger RNAs are ribosomes that are translating proteins. So perpendicular to that would be the proteins coming off. That's how the poor little bacteria have to struggle. In number B, or picture B to the right, this little pearl necklace type thing actually shows that you know, our messenger RNA, like the kind we take from exosomes or from Moderna vaccine, they can be read simultaneously. There are these little ribosomes that all of them are just reading the same message, and to the cartoon in C, it's showing this. So there could be 5, in this case there's what, like 20 something attached to one single message, and they're all translating the same message, and there are different stages of translating it. So the one on the left is just started, the one on the right in the cartoon has almost finished, and they're expressing proteins. This is the fundamental dogma of biology, that DNA codes for the message is translated by the ribosomes. So you can see here that you can introduce a protein, that's good, but a messenger RNA is much more important because it can be read over and over and over again and persist for quite some time. So the Kymera company is not just a fly-by-night company. They actually do scientific research on their product. And here's, they have companies that can put on a chip every known messenger RNA. I think it's like 14 to 16,000. And even now, the microRNAs, which are the blocking RNAs, which we'll go into. And you can see here that they've attempted to characterize this, in this case, through numerical histogram, what is expressed in their exosome product. And this is not a trivial task. You actually have, if you analyze, as one of the competitors did, the product of Kymera, and you send it to the lab, it'll come back as normal saline because all the contents, the business action, because of the way they're produced and isolated and purified, there's nothing in that vial but normal saline until you crack them open, like eggs or supermarket toy bubbles. Then you see what's in them. But if you send it off to the lab fresh and analyze it, it's just all you get is inert bubbles and normal saline, hopefully. So what you have to do, and why it's non-trivial, is you have to use a detergent soap. It's a standardized procedure, but nonetheless, it's a non-trivial step where you have to open up, dissolve the membranes in such a way that doesn't destroy the contents inside and denature the proteins and the mRNA. So as we see here, again, GDF11 makes an appearance, GDF15, the insulin-like growth factor binding proteins, which enhance the insulin-like growth factor effect. And we see our usual suspects, GF, granulite or growth factor, NGF, PGGF, SCF, yada, yada, yada. Page 2 here, a big spike here in tissue inhibitor metalloproteinase again. And on the right, we see our old friend telomerase, which is, I assume they mean human telomerase reverse transcriptase, which is the enzyme which lengthens telomeres on the ends of cells. Okay, so if you ever saw my first 8 foundational lectures, I use this analogy in addition to music. So you have proteins are like A, they're the gas, that's the message that's expressed. So that's good. And then you have the clutch, which is C, that would be like the messenger RNA. A clutch allows you to kick into high gear, right? So messenger RNA might be around for days to weeks and express that protein tens of thousands of times. So that's much more powerful than just the gas. And then the brake is the most interesting part, the part that's least understood. And again, every one of these proteins, people spend a lifetime studying PhD. So we could spend an entire couple of hours on just one of these proteins. But the point of what I'm bringing to you here is that we've known since the Nobel Prize for the Yamagata factors that if you just introduce these 3 or 4 genes, and you or their proteins that they code for, you can get a cell to pretend like it's brand new or de-differentiate. You can go back to a very primitive state. So there are de-differentiation blockers. In other words, in order to not become monstrous and de-differentiated, we have these tonically expressed proteins which inhibit our cells from acting young and over reproducing, right? If you're a jellyfish in the sea and you're going to live 1,000 years, you can get bigger and bigger and bigger because the sea is big, but we cannot keep on growing. So there's limits. And so that's why when you chop off a finger, unlike a salamander, we can't grow back a finger quite easily, but there are probably ways to hack that. But my point is, a microRNA is a very specific sequence of mRNA that will just fit like a lock and key on an existing message. So say you have a message that's saying, don't become immature and reproduce, or don't become stem-like. That's tonically expressed. And one of the interesting papers I cite in the nerve regeneration webinar is there's a microRNA that specifically blocks a blocker of de-differentiation. So when you have these microRNA, what they can do is actually block the blocker. So you're no longer expressing the blocker, and you can act immature and regrow nerves, and that's really exciting. So I think it's very poorly understood, but a very important aspect of what we're doing is the brake, which if you take off that inhibitor by blocking its expression, then for a while you can get immature and regenerative primitive behavior. Okay, finally we have again TIMP1 tissue inhibitor metalloproteinase. I just found this interesting because a lot of times I'll inject people in a problem area and they'll say, oh God, it feels better right away. I've never really understood how that would work because regeneration takes time. But apparently there is a pathway that metalloproteinases cause the inflammatory pain. So right on the spot, if you introduce a ton of TIMP, it can actually block that inflammatory pain signaling. Okay, this is super busy and I don't expect you to ingest all of it, but just remember when we talk about MSC exosomes only, I'm not talking about exosomes from cows or from cancer or liver failure. I'm talking about from MSC exosomes. Just remember, we're always going from 1 to 2. So 1 is TH1 is a certain flavor of immune response. and Th2 is another flavor of immune response. And then M1 is the type of macrophage which is inflammatory, and M2 is the type of macrophage which is not. So just remember, we go from T1 to T2, Th1 to Th2, and M1 macrophage to M2 macrophage. So just looking in the blue column, this is a bit busy, but in a nutshell, when you have Th1 activation along these lines, it's signaled again by interferon gamma, IL-2, tumor necrosis factor beta. This is the body ramping up for a huge threat, and it's very inflammatory. And these things are targeted by these anti-autoimmune drugs. So these things are very good for bacteria and viruses, okay, intracellular parasites, and it leads to a huge cell-mediated response. So people with activated Th1 systems, they can get things like lupus, rheumatoid arthritis, etc. Okay, so that's autoimmune is Th1. So we're going away from that, away from autoimmunity, viruses, immune responses, and Th2 is more for worms, helminths, okay? I know, why do we need that? I'm not sure, but that's just a different flavor. So when you're Th2, you're fighting things like hookworms, tapeworms, onchocercosis, these kind of weird worms. And it's a different flavor. This is actually a typo, I think, in the second line. It's generated by Th2 cells. Okay, so that's a different kind of thing, and that leads to humoral immunity, which means antibodies. Anyway, you don't really need to know that, but it is important to see above here that this is the whole cascade. When an antigen comes in, like a spike protein on a coronavirus, you have an antigen-presenting cell, and it does all these clonal expansions to not only create a humoral immune response, but a cellular immune response. So the humoral is more above, that's Th2. The cellular is more below, that's Th1. And then there's always memory helper cells. So next time you see a spike protein, you can mount a more vigorous anamnestic response. So again, T1, T2. In T1, Arnold was bad. He was there to kill the kid, Sarah Connor, I mean. And then in T2, he was there to protect John and Sarah Connor. So T2 is more protect, T1 is destroy, right? So again, just to sum it up, wrap it up, there are trophic growth factors in these exosomes. It's not random. And the whole point of the MSC stem cell, and I urge you to go back to Arnold Kaplan's lectures, who characterized it, who named them and wants to rename them to medicinal signaling cells, is that they are sent in to sort of like Harvey Keitel in Pulp Fiction. They clean it up. They clean up the mess. They start fixing and regenerating. T1 is there to destroy. T2 is there to regenerate. And that's why they have so many growth factors in them. Very poorly understood, but probably at the crux of a lot of this stem cell behavior is the microRNA that block the blockers temporarily. Again, when we go from T1 to T2, I have to always caution people to beware of HHV flares. Now, I just recently, 2 weeks ago, changed my consent to bold this and make it prominent, because if there have been any complications, they've been in human herpes viruses. Now, what are they? They're 1 through 7, I think. Common ones, HSV 1 and 2, oral genital herpes, but also in that family is CMV, Epstein-Barr virus, or chronic fatigue type things. It's argued that CMV is the cause of aging by grinding down your immune system. Varicella virus, or chickenpox, we just had a very prominent Hollywood A-list hyphenate actor, director, writer, and he got shingles. And had he been my patient and he called, said, "Oh, doc, I'm getting this tingling on my shoulder or wherever my face," we would have hit him with an antiviral, because this is a predictable side effect of going from a Th1 antiviral surveillance to a Th2. And so I really need to stress that if there's one complication, people with recurrent cold sores, they need to be continuing their prophylaxis. And if they are mindful that the first sign of tingling, numbness could be either a herpes or a chickenpox reactivation, we got to get on that. Also, body aches, rashes, nonspecific myalgias, these would all be of concern. And we could check liver functions. There's a lot of things you need to be mindful. So it's not just like, plug and play. You got to be a doctor about these things, and the patient has to give you a history. As I mentioned, M1 macrophages are in the early state of inflammation. They're governed by interferon gamma, tumor necrosis factor, and these other DAMPs or damage-associated molecular patterns. M1 is the attack, the reactive, the whole fire. And M2 is the anti-inflammatory mediated by IL-4 and IL-13. That's to shut things down, clean things up, tidy them up. So I think it's important as we end to say that inflammation, I used to not be of this camp. I thought inflammation was just the reaction to telomere shortening and cell suicide, which is a very inflammatory event. When a cell's telomeres are short, the cell knows it's damaged and kills itself 99.9% of the time. And it does this by using P53, which is the watchman of the genome. And you can read more about this in my first book, The Telomere Time Bombs. It pokes hole in those mitochondria, which leaks battery acid, and they melt like the Wicked Witch of the West from the inside. That's an inflammatory thing. But actually, there are many other things that can cause inflammation, and it seems to be part of the process of aging. Hence, some people like the term inflammaging. But also, throughout our lives, and we see this in the new challenge of this attempt to curtail coronavirus, we see a virus that has different mutations constantly mutating. And they used to say that the common cold, the flu were not curable, but now people seem to want to believe that. But we see these variants and there's mutations always coming up. And the point is that when you express a spike protein, the hope was that you can express it and develop immune response. But there's so many unknown unknowns in that are you really going to be primed for an autoimmune reaction next time you get the real exposure at a higher level? We don't really know yet. The data is not there. I was talking to my brother who's a pediatrician, and yes, he's seen cases of pediatric myocarditis. So, a healthy immune system is not the same as an old immune system. A healthy immune system will mount a response, and it can be ambiguous as to which way it will go. Perhaps in the greater scheme of things, it's better for society that some people be injured. But I think the patient-physician relationship is such that, people need to make their individual decision. Does this make sense for me as a 10-year-old to take this vaccine and express spike proteins to what end, given that the risk is so low? But that, unfortunately, has been politicized, and it's no longer at all about science or public health. Anyway, so the point is, I want to end with a positive note. Let's go. I'm going to stop sharing this, and we'll go to something that was fun. My sister sent me a video, and I'd like to share that with you. This is my 84-year-old mom. Of course, she's taken like 22 treatments. And actually, about eight years ago, she had back surgery. She had rods placed in her lumbar spine for excessive mobility and instability. And this is her showing off after the 6-year-olds were doing back bends. She did her little version of a back bend. I hope you can see that. She's doing a little wheel, but she actually drives with a handicap sticker. She had some real problems with her foot, with her plantar feet. And, she was in a lot of pain before 3 years ago when we started giving her treatments. And these treatments mainly focused on her brain, nasal injections. We also did shoulders a couple times. She used to not be able to sleep on her side. She had hip problems with her hamstring, her piriformis, her quadratus lumborum, which is more above the pelvis, quadratus femoris, I should say. We did epidural injection for her low back. So that was her doing a back bend. Here's her trying to do the splits. And mind you, she had chronic pain in her hip area. So it's not the greatest flexibility. For 84, I think you can see still not bad. And she's not hobbling. So she's feeling good about herself right now. And I think that she believes that she can live longer, even though her own children, at least 2 out of 3 of them, don't necessarily believe it. Anyway, so that's a good note. She firmly believes it's helping her stay less inflamed, less old, and helping her longevity. So again, not scientific proof, but something that leaves us hopeful. So at this point, I'd like to open up. I don't know if I'm going to get feedback from my speaker, but I'll open up to questions. I know that was a lot of science and it was really boring, but I think it's important to get your head around the minimal complexity of what we're talking about. Because people like to bandy about this idea of science and magic and authority. but it's very accessible to anyone who wants to understand it. There's the fundamental dogma of what we're talking about is very, very simple. And that is, oops, sorry. Ooh, it's playing loud music.
Yes, we are the best player ever to have 7.
Oh, okay, sorry, I gotta turn that off. Okay, anyway, the fundamental thing is right here to my left. DNA makes RNA, which is what makes proteins. Proteins, how they're expressed, where they're expressed, why they're expressed. That's the music that's being played. And all the behaviors, all the emergent properties of being a cell, an organelle, an organ, an organism, it all emerges from this whole game of what proteins get expressed and what don't and why. Okay, so let us close out of that and see if there are any questions. I hope I can hear you. And if you want to be unmuted, we got a hand raised. Alan, I'm going to unmute you if you will allow.
All right. Can you hear me?
Yeah. Were you able to see the video of my mom or not really?
Absolutely. Yeah.
Okay,
That was impressive. And I'm sold. I'm trying to figure out, as you know, how to get some exosomes from Chimera, which I'm hopefully lined up to do pretty soon. Great presentation as usual. It's so informative. It's really technical, and I can follow a lot of what you're doing because I've seen it before. But I'm counting on you to know that stuff and to tell me the results, and that's why I'm interested. I didn't go to school in Boston, so I don't know if I can keep up with you.
No, I mean, it's really, I mean, to be honest with you, before I started, I'm like, this is like a case of the one-eyed man, you know, because there's people who devote their entire lives to just one of these proteins. So I'm not an expert. I can just barely pronounce the names right sometimes, you know. So, but where the rubber meets the road is if you feel better. I mean, I guarantee you my mom doesn't know what GDF11 is, but now she can do a kind of a half decent back bend, whereas she was in chronic pain. So that's really what we're talking about. It's clinical medicine. It's heuristic. It's empirical.
Yeah, that what I'm like, both of us, we don't have like Dr. Ross's, what's the Chimera founder's name again?
Yeah, Duncan Ross.
Yeah, Duncan Ross. I mean, he studies this all day, every day. So, but I mean, my point is, it works. Your clients have something like what, 80% results.
I think it's somewhere around that, 78. Depends on what the endpoint for results is, you know.
Okay. Well, here's where I've learned some more as I continue to study. It turns out a really long time family friend is a doctor who's a spine surgeon, got really bad rheumatoid arthritis, was in a wheelchair at age 50, maybe in 60s. He's like really declining fast. And he found stem cells, went to Japan, one of the very first to do it out of the US. He's brought it back to the US. And what he does is, he gets the stem cells out of your fat tissues. They spin it and turn it into. He's recommending I take 200 million in IV injections, and then 100 million. These are stem cells. 100 million in my knee and 250 million in each shoulder. I've had some shoulder issues as well. So that's a whole different.
Since your treatment, hadn't it? So
it's been about 2.5 months, and I'm getting better and better.
Okay,
yeah,
good.
But before this is really expensive what he's doing, because to spin them into it takes like 6 weeks or something to spin them, and then they keep it frozen for the rest of your life, and they can always pull some out, spin them, turn them into hundreds of millions again. So it's a whole different ballgame than what you're doing. What I'm getting at is I quizzed the science there, and they said, well, exosomes are a very important piece of what stem cells produce. There's also 144 other vascular, many things that stem cells put out besides exosomes. So that one confused me. So have you heard about that or studied that or asked Duncan Ross about that?
No, it sounds vaguely biblical, like 12 times 12. I don't know. I don't know what else stem cells are putting out. I mean, maybe they mean within the context of exosomes, they're releasing other things. But as I just tried to explain to you over the last little bit, I mean, there are, many, many different signals of different kinds in these exosomes. This is quite the free jazz song ensemble. So I don't know what he's referring to, but it sounds kind of like, it sounds like it's a bit of a sales pitch, But
Could be.
the value proposition that we're kind of saying, even though this is not advertisement, is that we have something that is universally from a human being that is potent in terms of regeneration signals, and it's not going to be rejected like someone else's stem cells. Now, when you do, a couple of lectures ago, I did stem cell versus exosome. Adipocyte-derived stem cells are not quite mesenchymal stem cells. I mean, they're more rare, but you should get them from the bone marrow if possible. And yeah, I do know people who have frozen them, and that's legal. But to thaw them out and reintroduce them in this country is of dubious regulatory acceptance, shall we say. But people do it, and yeah, it's not prohibitively expensive. It's like maybe $500 a year, $350 a year to store them. So it's not a bad idea. It would have been much better to do it as a 21-year-old. But that is a good idea, because unlike taking it from a black sheep, like literally a black sheep or another person or another person's placenta, you're not going to reject your own stem cells. But as far as the 144 other things they can release, I'm not even sure what that means.
Yeah, they're what's interesting is they're here in Texas, we're in Houston, and Texas A&M there's a study they're doing with A&M, PhD people, and they're just studying exosomes and how it would affect Alzheimer's. So they're right in the middle of that and spending a lot of money on that. So they're big on exosomes, but just they're saying right now they do your own stem cells, and it's been working kind of like the same percentages as your patients, but it's in the tens of thousands of dollars, like 20 to 40,000. So it's that sounds
that's
like
a pretty big ticket item. Yeah,
it's real big.
I figure if you're getting a good result from exosomes, then it's going to be 10 times less, and so, like, for example, my Achilles, the three things I had were a torn rotator, a meniscus, and Achilles. And, I've done 2 injections the last 3 years in my Achilles, but I don't have chronic pain. I have full function, but there was a time when I couldn't really even use it. So to me, I don't like spending the money on myself. I think it's expensive, but I know I got that go-to. And like, my mom is a true believer. She can afford it. So she's had 22 injections, but like, she knows, if she has a wonky shoulder or something, if she re-injures it, she can just get an injection. It's all good. So I think it's just a tool, and I think it's a very powerful tool. And that's why I did that lecture on repeat injections, because most of my patients are repeats. Like, one of these guys who moved to Texas, it's a prominent guy there. He wants another injection because, we fixed his shoulder and his hip. So now he wants this other hip, But once you figure it's working, then you don't mind re-upping for a different region or a different reason.
Definitely. Yeah. Well, I'm not going to spend that kind of money. I thought it was interesting. I'm going to continue to learn. And like I think I mentioned previously, I've had hip, back, and knee. And I did the stem cells only, not exosomes, 2.5 months ago, and they're all 50% better. The hip actually went away.
Hey, that's a great result. Good for you.
So I'm going to get exosomes to follow up in maybe a month or two, and then before I spend that tens of thousands, if I ever do that.
I mean, ideally, ideally in the future, people on their 21st birthday will just get a bone marrow biopsy and freeze their stem cells. And throughout life, they actually have gotten pretty good at making the cells differentiate different ways into types of tissues. So you could take your own autologous stem cells, thawed and expanded. That's where the 6 weeks come in. They need time to expand them double to get tens of millions, ship them back to you, and then chase them with exosomes to turn them up, to activate them, to enhance their local effect and the effect on the stem cell. So this is the kind of the holy grail, if you will, literally and figuratively, when people 100 years from now will thaw out their own stem cells, get them shipped to them, injected where they're needed, and chase them with off-the-shelf placental exosomes. then you can just regrow your original equipment manufacturer parts as you get older and just stave off the whole process. Because, you know,
Yeah, that is the Holy Grail. That's interesting. I'm really excited about this whole field. I think in 10 years, everybody will be doing it just regularly, and hopefully be covered by insurance, but getting there, I'm going to, I'm real serious because this guy is a really good friend of mine. I mean, he's been a doctor his whole life, back surgeon, and what he improved. I mean, anyway, so he's 78 and he looks like he's 50. He's kind of like your mother, and he's,
Yeah. I mean,
so
you know,
anyway,
listen, yeah, no, it's great. I had a patient who went to Japan. They spent 50 grand to help her with stroke recovery, but it didn't really help. But we did 2 exosome treatments and she had significant improvement, but that's where the end of the road was for her in terms of improvement. So we just never know where the end of the road is.
At the end of my comment, I'll let other people chime in, but it's, I'm 63. So the idea is I'm going to freeze my 63-year-old stem cells and then maybe use them until I'm 80 or 90, hopefully.
Yeah.
I wish I'd have done it in my 20s, but,
It really wasn't
Anyway, we'll see.
available. Yeah.
right. Okay. Well,
I mean,
great to
better
see you,
than
Dr.
nothing.
Park.
Better than nothing. Hey,
Pardon
yeah, I might be getting my Texas license through in the next week or 2. So you might hear back from me in case I want to swing by Houston.
Please do. Like
Yeah.
I made a big pitch. Come set up in the Woodlands. There's a lot of great doctors up here that
All
would
right.
love to know you.
All right.
Okay.
Thank you, sir.
Thank
All
you.
right. Bye-bye.
Bye.
Any other questions, typed or you can raise your hand. Sorry, it was so technical. I feel like I had to do this webinar, even though it's not my expertise. But it's important to know that somebody has the answers, even though they don't really, nobody, including Dr. Ross, understands what the music means. It's there, but it's way, way early in the game to know how these things work. Maybe we'll never know. Again, I went to a lecture by the head of the Perimeter Institute, and he said the most complicated thing in the world is biology. It's not physics. Although I did have some questions about their whole dark matter idea. I think it's just a huge fudge factor, and I don't think they know what they're talking about. Any other questions, typed, or anybody want to ask a question? Thank you so much, Alan. Abby, how are you doing? Do you want to talk? Or Anne? Let's see if Anne wants to say anything.
Okay, can you hear me now?
Hey, Anne, how you doing?
Hi, I'm okay. I'm just, you know, I'm low on energy. Everything else is fine. I figured out the pain, and so that part's taken care of.
The knees are holding up on the 2-mile walks?
Yeah.
Good.
Well, no, 1 mile walk.
Okay, and the pain between the shoulders, that's still gone?
That's gone.
Good. And no more
And-
trips to the hospital? for
One more
heparin?
trip to the hospital, and
Alright.
they said that was all about pleurisy. And so I figured if I got out and walked or as much as I could, I would, you know, expand my lungs and do the heavy breathing and all that.
Pleurisy. I thought you were having irritation centrally at the windpipe. I didn't think it was as much.
Yeah. Well, I don't know. I was in such grief that I actually had myself airlifted to the
I
closest.
remember. Yeah, I think you might have had a minor clogging of your stent, and the heparin helped it. I think that was a
Well,
good
that's
move.
what I thought. Yeah.
Yeah.
That's what I think. But anyway, so if I get out and, you know, walk and expand my lungs and breathe deeply for a while, it's about a 20-minute walk. And if I can do that, I seem to be able to keep the pain off.
Outstanding.
Yeah, so that part's good.
How's your memory and focus? Is it good?
Well, I mean, that could always improve. I was sort of thinking of having you give me some more exosomes, you know, just for my heart, so I could get some energy back.
Yeah.
Because I'm told that it takes about a year to recover and get your energy back. So I'm certainly interested in doing that.
Well, you're really lucky that the heart attack didn't do anything more permanent in terms of the
Yeah.
actual myocardium. The fact that you had a normal echocardiogram, heart wall motion and function and ejection is super good. So I'm happy about that. I was
Yeah.
trying to get up there early to help you, but that's the earliest we could have arranged, I think.
Yeah, no, I understand. No, I'm doing fine.
Good.
Yeah, I'm running out of the recharge.
Oh, no
'cause-
problem. I'll send you some more.
Okay. Great. And can I pay you with PayPal? I can't remember.
Yeah, either way, I'll take a card or whatever, and we'll get you a dozen or so. Okay.
Okay.
All right,
Great.
Ann. Thanks so
Thank
much.
you.
Have a nice holiday.
You
Okay.
too. Bye.
All right. Anybody else want to chime in or ask a question? Now's your time. Okay, I think we'll call it there if that's the case. All right, everybody. Thank you for attending a rather sciencey lecture, but I hope you get the point is that these MSC exosomes are not just randomly expressing musical notes or proteins or messenger RNAs. The function of a mesenchymal stem cell in general is to guide regeneration, stop inflammation, and start the process of healing. And that's why they're such a good choice for our first exosome product that we're using. And that's why we're seeing pretty good response rates and pretty good happiness from the patients. So if you have any questions, you can feel free to email me at drpark@rechargebiomedical.com. And that website also has a lot of the links and blogs and other content that you can enjoy. So everybody have a good holiday, and we'll talk to you soon. Next week, I'll be in Las Vegas at the Anti-Aging Medicine Conference. So we'll see how that goes. All right. Thanks everybody for joining. Have a great day.